People that originally developed this method, they recognized that because of the symmetries that, sorry, let me go back up. Because of the symmetries present, if you look at each of these segments, it's self-symmetric. B12, B12, B16, B16, B26, B26 shown here, and so on for the D and the A matrix. You can use that and a lot of knowledge and time in your hands, and actually you can invert them. So the alpha matrix, which is at the top left, shown here now at the bottom, is given by this mess, which involves the inverse of the A matrix. So the exponent -1 here refers to inverse of a matrix, and a quite complex term here that involves, again, inverse of the A matrix and a whole bunch of terms that make up this new matrix, the inverse of which you have to take, and so on. Similarly, the beta matrix, which is the top right or the bottom left, will consist of this, and finally the delta matrix. Now, if you look at different textbooks, you may find, and typically you will find, different expressions for these. They all lead to the same thing, because depending on how you do this inversion, quadrant by quadrant, if you will, you can write these expressions slightly differently. So don't be surprised. Just make sure when, for example, if you need them in your homework, you might need them, you stay consistent with whatever equations you chose, because if you program half of the equations with one expression and the other half with another, they may not be consistent. You have to stay consistent with one set of expressions. Now, if the laminate is symmetric, we said the B matrix, the capital B, or the coupling matrix, is 0. And when you invert it, then the inverted matrix will also have a beta matrix equal to 0. So it ends up being in this form. And then instead of using the alpha matrix, we call it the little A matrix and the little D matrix. The reason is that in the general case, they are not the same. But if the laminate is symmetric, then they would be the same. So we created this construction, which theoretically appears reasonably interesting, but it has to have some relationship with reality. And so far, the only relationship with reality was when we said that force divided by cross-sectional area gives me the average stress, which I can relate to Nx. So all I have said so far is that somehow, in an obvious way, the loads relate to the average loads that we defined per unit width. But that is not even close to an attempt to design an actual laminate and come up with failure predictions. And to start with that, we have to think, what do we typically get in the laboratory as actual measurements? And the first thing that you know is that if I load something in tension and somehow I measure the stress, F divided by WH, my average stress, and the mid-plane strain, I would get, if all is well and the material is well behaved, a straight line, the slope of which is the Young's modulus, and that's fine. We are making some assumptions here. We are saying the laminate is not unsymmetric. The laminate is symmetric, so the coupling situation is pushed aside for now, just to make a point. So in the laboratory, we measure Poisson's ratios and shear modulus or Young's modulus, and everything we said here would be essentially useless if we could not relate our A, B, and D matrix with actual useful quantities. So let's see how this comes about. Let's take a symmetric laminate which is under uniaxial tension, which means Nx is the only load applied, and Y and Xy are 0. And if you look at relationship 1,6, which let's find where that is, so that at least, yes, okay, 1,6. Basically, we say it's symmetric, so the B matrix disappears. So I have Nx is A11 epsilon x0 plus A12 epsilon y0 plus A16 gamma xy0. That would be the general. And these now times those are not there because the B matrix is 0. Similarly, the Ny would be coming from the second row times that column. So if I go back, the first equation is A11 epsilon x0 plus A12 epsilon y0, and I'm neglecting the A16 gamma xy0 just to make the algebra a little easier. You can include it, and the final answer will have many more terms, but just to show the process. If it's under uniaxial tension, Ny is 0. So from the second equation, I can solve for epsilon y0, and what I get is I get this, which I can now substitute to the first equation where epsilon y0 is to get nx is a11 epsilon x0 minus a12 over a22 times another a12 that we have over there. So that's a12 squared epsilon x0. So if I factor out my epsilon x0, I arrive at the equation here in the middle that relates the nx with the epsilon x0. But we said before that there's a relationship between the average stress and nx such that essentially my force, instead of just saying it, we said, where is it? That sigma 0 is nx over h, and sigma 0 is also f over wh. So this is what we invoke here. And yes, we can move. Which will tell us that if I substitute for nx in terms of sigma 0, which is f over wh, I will get 1 over h, basically the stress. This relates nx, but nx is f over h. F over w. F over w is nx. So if I want to calculate sigma 0, I take my f over w and divide by h. But my f over w, which is nx, is given by this. So the right-hand side here has the f over w and the 1 over h coming from this term. So now I have finally managed to relate my applied stress to the resulting strain. And we know that